And next we'll have Dr. Nigel TAME from BHP. He'll talk about BHP's partnerships for steel industry's decarbonization. Dr. Nigel, please join me on stage. And while he walks, let me introduce him briefly. Dr. Nigel TAME is the head of steel decarbonization within BHP's marketing sustainability team based in Melbourne. He leads the company's efforts to develop low CO2 steel production pathways through partnerships with customers, technology providers, and R&D institutes. With a career spanning nearly 20 years, Nigel began at BHP Research and has since held roles in iron ore commercial strategy and technical marketing. Nigel.
Hi everyone, and thanks for the kind introduction. It's a real pleasure to be here today, and thanks to the World Steel Association for the opportunity to speak. BHP is also pleased to be a sponsor of the event. We had some people attend the last event a couple of years ago, found a very valuable discussion, as I have this last couple of days, so we're pleased to be here again and have a bigger presence in a speaking slot. As you know, BHP is a leading supplier of steelmaking raw materials, supplying iron ore and high-quality steelmaking coal from our operations in Australia, the iron ore coming from Western Australia, Pilbara region, and the steelmaking coal coming from our operations in Queensland on the East Coast. Today, I'll be sharing a bit about our Scope 3 steel decarbonisation program, the projects that we're working on, and how it fits into our climate change program at BHP. Please acknowledge the disclaimer. Luckily, you have a very big screen to read all the words. In terms of why BHP is involved in steel decarbonisation, we see it as that we have a contribution to make as a reliable, sustainable, and important supplier to the market. We have a role to play. We have a deep understanding of how iron ores and steelmaking coals perform in the iron making and steelmaking process. But at the end of the day, we're not a steel producer, so we can't actively or directly influence steel production emissions. So we are taking a partnership approach, and we have a way to contribute to this reductions in steelmaking emissions downstream in the value chain from our operations. So we've set 2030 goals around supporting technologies, developing technologies, and working with our partners to show how we can de-risk and support commercialisation, which is probably going to happen post-2030. We also have a 2050 goal that in the steel value chain, which is more directional. But importantly for BHP as an iron ore and steelmaking coal supplier, we want to understand the technologies that our customers will be using in the future and how to keep our raw materials relevant and value-adding in our customers' processes. So to work on this, we've structured a program that you can see sort of laid out on the right-hand side. The partnership theme sits across all of those approaches. We work with our customers. We work with research institutes. We have a BHP Ventures department which makes investments in startups, and we participate in broader ecosystems. I think one of the key themes I've seen in the last couple of days is really that multiple pathway approach to steel decarbonisation, and our program reflects that. And that's decarbonising the existing blast furnace process route, but also looking at new pathways, particularly for our Pilbara iron ores and how they can perform in those. And I'll talk a little bit more about those in the coming slides. In terms of those pathways in a little bit more detail, we have basically broken down into three categories. The modified blast furnace, which is decarbonising the existing process route through the use of CCUS in particular. We have the combination of direct reduced iron using our Pilbara iron ores and electric furnaces, particularly the electric smelting furnace, which you've heard a lot about. And lastly, the electrochemical reduction process route, which is more transformative, probably longer term, but we really see can play a role, particularly if you consider these multiple pathways have different economic sort of pros and cons in different regions with different contexts around energy, raw material mix, and regulatory environments. So I think it's been really pleasing to see that multiple pathway thinking across the last couple of days, and our program is certainly set up to reflect that. And we see all of these pathways have that roadmap towards a near zero CO2 intensity of steel production. So it's not necessarily trying to achieve zero. We've got to recognise there are a lot of residuals that have to be worked on, but really getting down to what we see is 0.4 tonnes of CO2 per tonne of steel. And since we've set up the program in 2020, we've gone through phases of setting up partnerships, doing studies, doing lab test work, programs, and really maturing the program across those three pathways. And in some cases, particularly in the optimization projects shown across the top for the blast furnace, these projects are at commercial scale and delivering real emission reductions with our customers who are hosting the projects. And that's why we build in the longer term demonstrations that are at pilot scale or smaller scale, like CCUS, and like the DRI work and the electric smelting furnace, which we're working towards pilot scale at the moment. We've also been working in electrochemical reduction to scale up different systems with our partners and understand the pros and cons of those different systems and the performance of our iron ores. Going into a bit more detail on some of those projects. For the blast furnace, I think this is now becoming a common understanding that the blast furnace pathway to that near zero intensity has the combination of technologies which include increasing energy efficiency, raw material blends, which includes higher quality coke, the greater use of lump and potentially pellets over sinter, to really step down that emissions by 10 to 20%. Then you have the recycling or carbon loop effect of the top gas recycle back into the blast furnace to step down even further to about 50% reduction. But to really get down to that near zero intensity, you need the carbon capture and utilisation and storage. And within the integrated steel mill, there's multiple point sources that you can apply that to. Each have their own profile in terms of gas composition, impurities, and different technologies may or may not work. So it's important to understand where those point sources are and the cost and the risks around applying those. We also have been doing research with our University of Newcastle team to look at if you're injecting hydrogen into the blast furnace in different stages there, what impact does that have on operations? So building more models to understand where the operating environment might be best for hydrogen, looking at the materials performance of coke and ferrous under hydrogen environments, and then trying to validate those at commercial scale through our partnerships with our customers. The example shown here is the EMSTEEL project in China for coke oven gas injection. And some early learnings coming through is really that high quality coke can play a key role in resilience against hydrogen attack. And then there's some trends in the ferrous burden RDI that we're seeing around the impact of hydrogen on pellet degradation versus sinter and lump, but we've got to understand that a bit further. Ultimately, we see the raw materials will play a role in that decarbonising the blast furnace, and high quality coke is going to be very important as you're trying to reduce fuel rates significantly. So understanding the performance of that coke and the coals that go into it and how you generate that quality is important. Dipping into that Zenith project a bit more, we've got some initial results. The coke oven gas injection was constructed and commissioned recently after about a 12-month period. The initial trials being run by Zenith are very promising. We're seeing the coke rate coming down a bit and obviously leading to CO2 benefits. But it's still early days and they're still doing more trials to optimise that further around the application of which tuyeres and the injection approach as well. So hopefully with them I'll be reporting more results in the coming months around that project. But it's a good example of that real reduction in CO2 happening with our partnerships with the customers. In terms of carbon capture, we don't understand, I don't think anyone understands yet, which carbon capture technology might work best with different point sources in the steel mills. So we're really looking at a range of technologies in our portfolio and at a range of different scales, trying to answer different questions, essentially. So if we take the example of our project with ArcelorMittal and MHI at Ghent, it's a small pilot, but it's using conventional amine technology, which is proven at scale, but in chemicals or cement plants or power stations, not at the steel plant. And so we're really trying to understand the performance of the blast furnace gas capture with that technology. So it doesn't need a big plant, so it's very focused. And we're hopefully going to be reporting some outcomes for that in the coming months. With HPIS, we have a slightly larger plant looking at PSA, again, a different technology, seeing how it can perform with the blast furnace gas. It's not just the static composition or the average composition, it's the impurities and the minor components of that gas, but it's also how it fluctuates during production periods as well that has impact on potential capture. And we're looking to really understand that. Larger scale with JSW and Carbon Clean and in India, we're doing a study at the moment for a larger plant. They're lucky enough in that region, there's a market depth for the captured and processed CO2, so they're able to look at a larger scale module there, and really that'll be a lead project for the industry, and potentially innovative carbon capture amine technology with a cyclone CC provided by Carbon Clean. We also joined a CCUS hub study with some of our customers and other value chain participants in August, and we've really found that the problem doesn't end at the steel sort of boundary, steel plant boundary for CCUS. What happens after that is really important, and actually our customers and ourselves, we don't really know that. So it might not be the most economic solution, but you really have to characterize that and understand where the options are and what things need to improve. So this hub study is helping some customers of ours in Asia really prioritize where those storage options might be and what levers are needed or what instruments need to be developed to improve the economics of that for CCUS to be a solution for the industry. In terms of the new pathways for Pilbara iron ores, before I go into some case studies on that, I really wanted to touch on that topic that Gessa was sort of talking about in the last speech in a conceptual sense, because this question around beneficiation versus downstream improvement or gang removal is really important to understand. So we've got this chart on the left-hand side, and it's only an illustration, it's not real data, but it sort of tries to illustrate the concept. The green line shows a standard iron ore that responds to upgrading and can produce DRI grade quality. As you move from right to left up the chart, the grade improves, you would lose mass, you lose iron, you create tailings, you use energy, you use water, but ultimately you can get to that grade that the EAF can accept after DRI. The orange line is the Pilbara iron ores, and even though you can try and upgrade it and have some benefit, you keep losing mass, you keep losing iron, but you never quite get to the DRI grade. And this is the conundrum. I think as iron ore suppliers, we'd love the beneficiation to work, and we're always going to study new ways of doing that. But the reality is the gangue minerals are so well integrated into the iron matrices that you just can't liberate it. And you can spend a lot of energy and use a lot of resources to try and get rid of that. But ultimately, you're fighting nature there. So, of course, we'll keep looking at it, but this is the reality that we're dealing with. And under any scenarios that we think is plausible, Pilbara iron ores are going to play a role in the market. So it's important to understand this constraint and why we look at the ESF on the right, which looking at that flexibility and able to take a wide range of iron ore feed materials and produce a wide range of steel grades at the other side. There was some conversation in the last discussion around the pelletizing, and we have been doing a lot of work around this. 5 years ago, we were told, and we had the same mindset, Pilbara iron ores can't form pellets. And there are some constraints, but like sintering, which has been the long mainstay of the process for the use of Pilbara iron ores, there's ways to improve the performance. And actually, we find that the steel producers in China are more readily in growing the use of Pilbara iron ores in their pellets as a blend material. Up to 40% in blast furnace pellets is kind of normal for some of our customers now. And we're really trying to work to understand how to increase that ratio through pilot testing and then into commercial trials. And some of the things we're learning, I think it was sort of touched on by Gessa, but the actual pellet grade on Pilbara iron ores achieves around 63 or 64% iron once you get it into the pellet, because you're losing that iron, that hydration water in the agglomeration process. So you get a concentration effect of the iron going from a Pilbara iron ore to the pellet. So that's important. It's a simple concept. I think everyone should know it, but it gets lost in the noise sometimes. Pilbara iron ores are easy to grind, particularly with dry grinding compared to other iron ores, and good balling characteristics. Generally lower binder consumptions. In terms of the optimization, we've got to really work hard on the induration temperature profile and the fluxing and which blend partners. And we haven't fully worked that out yet, but we're having success going from 10 to 20%, which we believe you could probably maintain a reasonable EAF production, blending our iron ores into the pellet. We've achieved 30% of the Pilbara iron ores into the pellet for DRI shaft production, and that's performed well, and I'll talk a little bit about that next. We've also tested at labs and pilot scale 50 to 100% Pilbara iron ores, and it's more challenging. There's a quality impact, but we're working through that as well. This is also using commercial plants which have fixed designs and operations linked to downstream production. If we're able to get in early and talk to those companies developing pellet plants with Pilbara iron ores in mind, there's potential benefits there. And so we're open to discussions with those kind of parties or equipment suppliers who are thinking like this as well. In terms of those DRI shaft trials, we've been successful working with our partners in China to complete full-scale tests around 2 weeks at a time using Baowu's Zhenjiang steel, which is around 1 million tonnes per annum scale. Basically using a pellet blended with different hematite and magnetite with our Pilbara iron ores, and the DRI shaft operation was smooth, DRI quality was good, and it was able to be blended into the BOF with hot metal and scrap. So a good outcome, and the next steps really are there to take that Pilbara ratio higher in the pellet and then do the same sort of commercial scale trials. In terms of the electric smelting furnace work, we started lab work. We saw the opportunity to start characterising and understanding the system. So our team at University of Newcastle in Australia started setting up lab facilities to look at that, the performance around the electrode, looking at small scale around 5 kilos, batches, and really learning a lot around how the formation of metal and slag, how elements are partitioned, and also the deportment of carbon into the system. So it's an ongoing process, but it's really helping to build that understanding, not only of the system and how that feeds into pilots and larger scale, but also the experimental technique is really important. Developing those analytical approaches is really important. We found some of the facilities these guys have been working with, they don't have the capability anymore because the investment hasn't been there for the last couple of decades. So we're really trying to help build up that capability. In terms of other activities, we're involved in the NeoSmelt project, which Chris Page spoke to earlier. That's a key flagship project for us in terms of taking it to the next scale and learning more in terms of which forms of DRI, where it's charged, how you achieve the metal and slag outputs, and then how the larger operation performs. We're also advocating for DRI ESF technology through programs in Australia like the HILT CRC and others as well. So we're really trying to build a program which supports different scales and understanding different elements of the process towards commercialisation. And lastly, just on the electrochemical reduction, we're participating as investors in Boston Metal, which is molten oxide electrolysis at high temperature, also Electra, and both of these are in the US. Electra is at low temperature. We test other systems where we're looking at molten salt electrolysis with the University of Newcastle. So we're trying to understand how those different systems perform and their potential pathways to scale. I think these, particularly with Boston Electra, we see that there's analogues. Boston Metal is similar to an aluminium smelter, obviously a lot higher temperature, but you can sort of conceptualize that it can play a role in mainstream steel production in the longer term and maybe open up new markets and geographies for steel production. Electra is a bit more like copper electrowinning, and we could see that something like that might operate more efficiently in a remote location compared to an integrated steel mill or a fluid bed DRI furnace as well. So we'd really try to understand the pros and cons of the different systems and importantly, how our iron ores perform in those as a feed material. And so far the lab scale work is really, really promising and we're looking to continue that work. So just to wrap up, BHP is participating as a value chain player in the decarbonisation of steelmaking. We see multiple pathways. There's no single solution. I think that's an important message that's come through these last couple of days, and it's really pleasing to see that we have aligned views on that. Some technologies are closer to deployment, and we're working with our partners to demonstrate those potential reductions to the blast furnace, but also looking to the future and doing the pilot work with our partners on CCUS and hopefully in the future top gas recycle. And we're also looking at these new processes and how our Pilbara iron ores can play a role. And we see that partnership is really essential for this process, and BHP is looking to play our role and support the industry in de-risking and understanding the technology, the developments that need to happen, and how they can be optimised as our customers seek to build these processes into their roadmaps in the future. Okay, thanks for your time.
Nigel, quite an extensive decarbonisation portfolio, I should say.
Yeah, we have a lot of projects. Actually, focus is really important because there's multiple pathways, but there's a lot of variations within those, and we have to really focus on what's going to be suitable for mainstream steel production. We're a large producer. We can't be playing around on the edges on too much stuff because what we look at has to be suitable for hundreds of millions of tons of steel production, essentially. And that's how we help focus. Yeah.
Yeah. And also quite impressive progress so far as I can see.
Yeah, so far so good, but it's all about the partnership. Yeah.
Yes, yeah. Yes, perfect. Yes, the key word is partnership. So, any questions for Nigel, please? Yeah.
Thanks a lot. I have some questions about the slide 8. Okay, so it was about the progress that you are doing in the blast furnace, that I'm really happy to see that blast furnace is not so demonized anymore. So, you mentioned that with top gas recycling, energy efficiency, raw material improvements, and carbon substitution, you can reach around emission factor 1?
Yeah, that's what we estimate. I think
Scope 1, 2, 3?
Yes, yes.
Okay, and which is the TRL of this process right now?
So the TRL is actually, I think, almost commercial because you have Baowu working on the Hycroft technology, which has been operating at a 400 metre cube blast furnace in Western China, and I think trialled on a larger blast furnace in the same location. So we feel quite confident that that process can work. It's about probably around how it can be optimised and rolled out to larger blast furnaces. And the Course 50 work, of course, in Japan is reflecting that technology as well.
And an idea of the cost comparison between the pig iron coming from traditional blast furnace and this optimized blast furnace, which is the cost comparison, more or less?
The cost comparison? I think some of those optimization steps are cost positive, actually. They're NPV positive. And that's because they're reducing the energy consumption or they're increasing productivity. So some of those are actually NPV positive, and so it's really trying to understand how they can be brought into the process.
Thanks a lot.
Other questions? Nigel, maybe I can ask, you mentioned blending Pilbara iron ores, and through that achieving how we called a good DRI shaft performance. So by blending, do you mean blending Pilbara iron ores or blending Pilbara iron ores with non-Pilbara iron ores?
Yeah, blending with non-Pilbara iron ores.
Non-Pilbara iron ores.
Yeah.
Okay.
So because the Chinese steel mills have the pellet plant on site, they have the flexibility to create whatever blend they want. And this is really analogous to how our customers have used the sinter plant. So we're really trying to take that thinking into pelletizing. Yeah.
There's a bit of a difference when compared with the current pelletizing operations. So these pelletizing operations are at steelmaking site.
That's right.
Okay,
Yeah.
okay, okay, interesting. All right. Any other question for Nigel? Yes, please.
Do you see only pelletizing as a pathway for Pilbara iron ores, or do you see also the fluid bed as a pathway?
We do, yes. Essentially, we know that works. We had the DRI plant in Port Hedland based on fluid bed technology back when we were a steel producer. So we know it works for Pilbara iron
20
ores.
years ago.
Yes, but we learnt a lot about that process. But we definitely know it works for Pilbara iron ores, and also POSCO have mastered this technology as well. It's about whether the system can work at scale with hydrogen. So it's a different sort of technology risk that we're trying to deal with there. But definitely, yes, we see that. Yep.
Any other question?
Stefano?
Yeah, I think I see a hand over there.
Thank you for the presentation. I've read recently an announcement that you have produced together with Binding Solution an agglomerate. Is this agglomerate ready to be charged into a DRI reactor?
I don't think that was us, but I know other Australian iron ore producers are looking at that binderless solution.
It was Pilbara.
Yeah.
Sorry.
We have looked at this technology a while ago, but obviously the devil is in the detail about how you get that binder to be effective. I think the cold strength is fine. The hot strength is where the challenge is around that. But also, are you bringing a lot of waste material into the process through that binder? Is the curing time going to kill your productivity? Things like that. So we're a little bit on the fence around that technology, but we're happy to see someone use it and do well with it and learn from that if that's the case.
Okay, I cannot see any other hand. Nigel, thank you so much for the
Thank you.
very valuable presentation. Thank you. We are finally leaving Australia, but coming back to the digitalization topic. Next, we'll have Mr. Narottam BEHERA to speak on integration of machine learning and metallurgical insights for sustainable electric arc performance. Let me introduce Mr. BEHERA very briefly. Mr. BEHERA is a metallurgical engineering professional with over 23 years of experience in operations, R&D, and project management. Currently with EMSTEEL, he previously served as a lead scientist at SABIC and held positions at JSW, ISPAT, and Tata Steel BSL. He is currently pursuing a PhD focused on AI in steelmaking. Mr. BEHERA, please. Thank you.
Thank you, Chairman, for a nice introduction. Thank you, World Steel Association, giving this opportunity to present our work. So this is AI-driven optimization framework for EF operation. So I will like to give a brief introduction about the EMSTEEL. EMSTEEL, we have a DRI-based EF, and we have 3 electric arc furnace, 2 150 ton, 1 is 55 ton, and we are producing rebar, wire rod, heavy section, and sheet piles. So I will give the overall decarbonization strategy of EMSTEEL. EMSTEEL, if you see, they are the leader in decarbonization strategy, and we also get award from the World Steel, and we are reduced our CO2 emissions drastically, and we have a very challenging target. And we are planning to reduce our CO2 emission by 2030, which is around 1.9 metric ton of the total absolute. And currently we are, if you see, we are far below the world steel, which is around 0.97, and if you consider scope 1 and 2, it is 0.67. And we have a challenge to net zero by 2050. So if you see what we have done several things, increasing renewable energy, then we have first worldwide CO2 capture, and we have also implemented the pilot, first MENA green hydrogen pilot project. And now we are working in several areas, which is electrification, then energy efficiency, digitization, and use of recycling of the scrap, which is further to reduce the CO2 emissions. So if you see, basically I will speak about the more detail about the electrical furnace, how we are optimizing. If you see electrical furnace in DRI, there is a current challenge that currently we have a DRI furnace which is produced 250 tons per hour, and we have electrical furnace 150 tons per hour. And we are continuously feeding hot DRI, and the capacity of transformer is 130 MVA. And if you see, we are around tap to tap 40 to 50 minutes. So the current challenge is now there is no real-time DRI analysis, and also we don't have continuous bath temperature measurement. So if you see the plot here, the operator, when continuously feeding the DRI, they face the challenges due to non-availability of online temperature measurement. Whenever you take the temperature, it's around 30 minutes, and sometimes temperature is higher. And that will be a loss of energy, and that will be end. If you already temperature highest, then he tried to reduce the DRI feed rate to control the temperature, which is impact of the productivity. So which is have energy loss, productivity loss. So here idea is that how to optimize this and what are the things to be done so that we will have optimized process. So if you see, I will go more detail about the modeling. If you see the modeling, there is initially, if you see 1970s, we started with the modeling of the EF. Then we start the CFD era, which is ANSYS, Fluent, and other things. Now after that, if you see 2020 to 10 to 16, we have compressive heat balance, mass balance models. Then we have hybrid model. Then now the era is machine learning. So even if machine learning, we have a lot of challenges. Because in machine learning, if you see, there are a lot of machine learning model which is black box model. This is not explainable. And another thing is that machine learning, where you will do machine learning, it will predict. But there is another challenge of optimization with the controllable variables. So that's why the now era is hybrid modeling, where you will mix the machine learning with the physical model and fine-tune the physical model using the machine learning to optimize. Then there are different optimization algorithm is there. So in my study, I am using the genetic algorithm. So we will go detail about what is genetic algorithm. So if you see hybrid modeling, basically it is a combination of machine learning model, then optimization using genetic algorithm. So it will be a real world data-driven modeling with implementable process, which is a flexible and sustainable process. So if you see how we are going to deploy this, because we are already have a platform, digital, so we want to deploy our machine learning models in our digital platform. We have a PLC level 2 data and we have EBA data, which is a time series data. We are connecting to the furnace things. Then we have putting our machine learning and optimization model to control the controllable parameters. This is our main aim. So though we are making the model with more variables, but we are only trying to control the controllable parameters where we can achieve the benefits. So we have also done the mass energy balance calculation. If you see, this is based on our furnace, but with maintaining some DRI temperature and carbon, because you know DRI temperature and carbon is a link. So if you want to optimize the DRI, increase the carbon, your temperature, DRI temperature is down. So based on, there is a multi-objective optimization we will need to work here, where we have to optimize both DRI carbon and DRI temperature. If you see the energy losses, here we need to work. Because if you see in the flue gas, we are around 226 kilowatt hour per ton we are losing. And in the slag also, we are a loss of 57 kilowatt per ton, which is a huge loss. So we need to spend some research to implement some of the waste heat recovery, then energy capture from the slag to reduce the overall energy consumptions. So I will go more detail about the machine learning model design. So what we have done here, we have collected the data because DRI furnace data is not online. The lab analysis, we are align the lab analysis with the respective of electric arc furnace heats, because lab analysis is not a continuous. DRI is a continuous process, whereas electric arc furnace is a batch process. So we align both the data. Then we have done the data processing, data removals. Then we have using different algorithms like linear regression, decision tree, support vector, Gaussian process regressions, and Cornell and artificial neural network. Then we evaluate each model. Then after that, we analyze the R-square, which is coefficient of determination, root mean square error. Then we have each model, we compare the performance of the model. After comparing the performance of model, we validate this model performance with the metallurgical process variation. Though some of the models having higher accuracy, but it does not follow the physical phenomena. So we are not considering as a right model. So we are combining the machine learning model performance with the metallurgical variations, then consider as the best model. Then after developing this model, we are putting in optimization algorithm, which is called GA, genetic algorithm, to optimize the process to minimize the energy. We take parameter like suppose in the electrical furnace, we have 4 parameters controllable: oxygen injection, carbon injection, lime and dole lime. Whereas DRI, what is coming, this is not in our control. So we are maintaining the dual quality. What are the best parameter to optimize the energy, minimize the energy? That we have done. Then if you see, we have run different feature selections, which is a machine learning tool like MMR, R-square, R-relief. Then based on this machine learning algorithm, we compare best performance of the features which is impacting the process. Then also we validate this feature which is on the metallurgical process. Like in the electrical furnace, active power is the most important factor to control the energy. Next, the hot DRI temperature, hot DRI quality, and the our oxygen injection. These are the most important parameter which is controlling the energy. So though we run different feature selection as per machine learning, we validate with the metallurgical process which is the best feature selection which is suitable for the process. So we choose R-relief process. Then this is the comparison of the different model performance. If you see here in both the cases, arcing time predictions and energy prediction, Gaussian process regression having low R-square, RMSE, higher R-square, low RMSE and ME. So that indicates this having model validate which higher accuracy level. Then if you see, this is the actual versus predicted specific energy. We have plotted the S-curve. What is the benefit of plotting the S-curve? That we want to capture, even if in minimum and maximum position, it is follow the trend or not. So this model having R-square 0.9, which is very high accuracy, and it follow the trends of the actual measurement. Similar thing we have done for the arcing time predictions. It follow the arcing time predictions. If you see actual and predictions, it is well follow, and we have done for the 1 year data analysis, which is around 9,000 to 10,000 hits. This is also we have done for the slag chemistry predictions. Slag chemistry prediction within the, because we are not analyzing the slag chemistry for each heat. What are the heat available for the 1 year data? We have done the model for the slag chemistry predictions. Then if you see, after predicting the model, we have done a correlation coefficient plot, which is a sensitivity analysis. What does this mean? We fix one parameter and we fix other parameter, one parameter varying, changing the energy. So if you see DRI FEO, which has an impact, because these plots are normalized in both axes. So if you see DRI FEO, if DRI FEO is increasing, your energy is increasing. Similar thing, DRI is silica content, increasing your energy is increasing. Hot DRI temperature, increasing your energy, decreasing. So we match the model result with the physical phenomenon of the process to validate the process. Whereas in the oxygen injection system, if you see, this is a plot where after some time it has an impact negatively to the process. So if you are putting excess oxygen, it has a negative impact on the process. It reduces the yield, it have more oxygen, ppm, tap oxygen, which have impact on the ferroalloy consumption. So that are negative. That model capturing the physical phenomena of the process. Then if you see, we will go to the what is genetic algorithm. Genetic algorithm is based on the Darwin theory of natural evolution. What it happens if the genes of the parents go to the next generation, the best gene transfer to the next generation. This theory works like this. So if you see, the first method of this initiation, what we have to done? We have to do the population size, how many population you are taking, how many genes you are considering, what are the crossover factor, so what are the mutation rate. So these are basically evolutionary optimization technique which based on the Darwin theory. So where we are considering as a fitness function. What we have done here, the model what we developed, this model consider as a fitness function to predict. After that, what we have done, we consider, suppose we have considered 8 input parameters in the model. Out of this, some parameter which is not controllable, we consider as a fixed variable. Which parameter which under control by the operator, we consider as a variable parameter. So, we put the same range, minimum maximum range of the optimized value to run the genetic algorithm to minimize the energy. And here, if you see, this will optimize the oxygen injection rate, carbon injection rate, lime and dolomite injection rate to minimize the energy consumption. It runs more than 500 times in one hit to still reach the global minimum. There are two types of minimum. One is local minimum and global minimum. Some algorithms which is optimization, this talk in the local minimum. Whereas this genetic algorithm reach with the global minimum. So that means it is the algorithm which is complex, solve the complex problems. So if you see, the DA did not get in the local minima, it will keep on the global minima. And another here, if you the result, we divided the result actual and versus optimized. So some of the cases, the GA does not reduce because it is already optimized. Some of the cases, it try to reduce the energy so that, and based on the energy reduce, it select the what are the 4 parameters which can be controllable, which will reduce the energy. Then after this result, we consider the whole year data, it is around, we are able to reduce for the 10 kWh per ton of steel, and 7, you can consider 7 tons per hour productivity, and which converts, we are converting to CO2 emissions based on the countries compared to the KSWS to CO2, it is around 10 kg of CO2 emissions reduced per ton of steel. So if you see the conclusion, to develop a robust hybrid GPR and framework, delivering high accuracy prediction with specific energy, arcing time, and slag FO predictions. Domain input feature selections and sensitivity analysis was strong alignment with the metallurgical principles. G optimization achieved 10 kWh of energy reduction, 7 tons per hour productivity, and 10 kg per ton CO2 reductions. All optimized recommendation was validated within real plant operating constraints, ensuring practical and safe implementations. Then outcome, traditional thermodynamic models may be capture real-time variability and complex non-linear interactions, forming scalable foundation for the industry 4. So future work, we are extending work in the LSTM model, which is long-term short-term memory, which is trying to get the online predictions with the consider as a sub-center for the carbon and temperature prediction online, because now there is a challenge, there is no online predictions. So we are developing online predictions for carbon and temperature. Then we are developing a digital twin considering both temperature prediction, carbon prediction, tapping oxygen ppm. Then we are also working on the multi-objective optimization. So what till now we work, this is a single optimization problem. So we are trying to do the multi-objective optimization where we want to consider three things: energy, productivity, and CO2 emissions. So this problem we are trying to working on this, and this is help us to industry for integration. And this is the reference. Thank you for your time.
Narottam, thanks so much for the impressive presentation. Quite intensive digitalization and modeling work done at EMSTEEL. So any questions for Mr. BEHERA? So perhaps I can kick off the questions. So in your experience after all this intensive work, so what are the key factors to the success of this line of work? Is it the sensors? Is it the modeling know-how? Is it, which factors?
A key factor here is data. Because modeling, if you have a real data and right data, then it is very easy to implement and the right platform to implement. Two things. Modeling part is, I think it's okay, but most thing is data. If you have a proper ecosystem where you can collect the right data, then you have a proper platform where whatever the machine learning or physical model you are developing, it will be implementable. So we are trying to, we have done most of the investment to have industrialization. So where we are collecting most of the data, real-time basis. We have installed EBA server in all the plants and energy meters. And the same times also we are invested in Siemens Edge platform where all the digital model could be implementable. So this is the two key factors to have a digitalization.
Thank you. Thank you. Impressive. Any other questions for Mr. BEHERA? Okay, so thank you so much
Thank
for
you.
this very valuable presentation. Thank you. All right. Last presentation of today. Maritime transportation results in emissions of about 1 billion tons. And iron ore shipments account for 6 to 8% of that. So it's also a challenge to decarbonize the iron ore shipping. And we'll have a presentation addressing this challenge. May I please invite Alexandre Salomao and Ms. Michelle Gonzalez from Vale. Alexandre is a manager at Vale's Innovation Department with over 20 years of experience in engineering and R&D. Holding a Master of Science in Power Systems, he leads innovation portfolios and strategic partnerships across Vale's iron ore operations and research centers. And Ms. Gonzalez is the Senior General Manager of Shipping Commercial Business and Operations at Vale. Michelle is an active advocate for sustainable partnerships between charterers and ship owners, championing causes from inclusion to industry-wide decarbonization. So Alexandre, Michelle, please, stage is yours. Thank you.
First of all, good afternoon, everyone. Thank you, WCA, for the opportunity here to be here in the space to present. As the last presentation, we'll try to keep you interested here in presenting our shipping and the innovation journey on the shipping area. Shipping is a very important link between our mine sites and also the steelmaking industry. Shipping is part of Vale's Scope 3. And today will show, together with my colleague here, Michelle, what we are doing and what we are developing in partnerships to reduce the emissions for this operation. Okay, let me go here. So this is the disclaimer, and here we have some information, and what we present here you can access in our website and our public reports. Following that, decarbonization is an integral part for Vale's strategy. Today we have mainly 3 pillars in our strategy. The first one is to be a trusted partner. It's the connection between the company and also our stakeholders. A superior portfolio is the second pillar that related with the products and the products that we sell and you provide for the market. And the third one is the performance-driven. It's a pillar that we work on the innovation, culture, and very specifically the safety. So I would like to highlight the two main topics on this slide. So this is about the generating positive impact. It's totally linked with the decarbonization and also fostering the innovation and digital solutions. This is part of our culture and what we are developing now in Vale. So just to point here, since 2020, we invested more than $1.4 billion in decarbonization initiatives. Just last year, more than $250 million for decarbonization initiatives. Following this timeline, this is our commitments, our goals on decarbonization. The first step or the first goal is to reduce our scope 1 and 2 emissions by aligning with the Paris Agreement, reduce 33% of our direct emissions. The next goal is to reduce in the scope 3 15% of our emissions by 2035 and be net zero in emissions for scope 1 and 2 in 2050. Additionally, we have another two goals. One is the energy transition, related to energy transition. All the electricity that we consume in our operations will come from the renewable sources, and this is a goal by 2030 globally. We reach this target. And the last one is the nature-based solutions, so to protect and reforest 5,000 hectares, 5,000 hectares of forest and the nature. Where we are on this pathway, so for the scope 1 and 2, we already achieved around 27%, 26.9% of our reductions based on 2017. This is our target. For the scope 3, we are already reached 13%, 13.2%. And for the energy transition, in Brazil, all our operations are, the electricity that we use in our operations came from renewable sources, and we mainly, we achieved 80% of our renewable sources in using electricity in our operations globally. And the nature-based solutions, we almost have 220,000 hectares of forests protected and reforested, on top of 1 million hectares that we already protected in Brazil and in our operations. Okay, so this is our talking about our green gas emissions at Vale, our profile. This is what we are today. So for the scope 1, 2, and 3, so scope 3, it's related much more of our direct emissions. It's 98% of our total emissions, but talking in the right side here, so the scopes 1 and 2, more than 40% are related with our mobile combustion. So this is the fleet that we operate, and mainly locomotives, trucks to transport the ore in our mine sites. And almost 50% it's our process, pelletizing process, furnaces and heaters in our operations. Looking for the scope 3, 95% is related with our products, the sell and products for our clients, and 5% it's the upstream and downstream operations, and so shipping is 3% of that. And we'll talk later more in details about that. Before we go to the shipping, I would like to highlight how we are organized and how we approach the innovation in Vale. Today we count with more than six R&D centers for iron ore. We have more than 500 R&D and innovation projects ongoing in the company. Those projects mainly, or a big part of that, we do it with universities and in partnership with companies. And we also have 15 innovation hubs, hubs that are linked or connected with our operations to support them with methodology, support them with connections with externals, to have a different approach for the innovation. We organize and these 500 initiatives in 12 innovation programs that we call our programs that cover all the value chain, from the exploration to the operational asset management. So we cover all the value chain. And as you can see, we have the two focus here on the decarbonization, Ecoshipping, that we will talk later, and also decarbonization solutions that cover scopes 1, 2, and 3. Talking about the scope, the decarbonization solutions program, what we are doing today, mainly we are focused on the alternative fuels. In Brazil, we have a good opportunity for that, but we also work on this for the shipping that we presented, electrification, and also adoption of technologies and low-intensive technologies and fuels. For the eco-shipping, we also working on this area, but I will hand over to my colleague here, Michelle, to present and detail for you what we are doing on this important program. Okay, thank you.
Thank you, Alexandre. Good afternoon. Okay, just to go straight to the point, what is the Ecoshipping program Vale? The Ecoshipping program basically is a program focused on the shipping business, which is the main supply chain for delivering the product to the clients. And those programs, it's a focus on innovation, which is reducing the utilization of heavy fuel oils and accelerating programs that focus on energy efficiency of the vessels. So the Ecoshipping program have the main focus of capture innovation and test, verify, certify, together with several institutions, and basically is to accelerate what the industry needs to move forward. Okay, why we focus on that? Why that's so important to us? Because of the map. If you look at the map, our supply chain is one of the most complex. We are very far from most of our clients, and it means that we have to use innovation. Innovation is crucial for element for our competitiveness, and it shows in the map how we position ourselves in South America, and we distribute along several different points in the world. Shipping, of course, and it participates on the Scope 3 of Vale, and the initiatives are fundamental for Vale global decarbonization journey. Well, the Ecoshipping program, now we're talking much more about it, but this journey started long ago. It's over 15 years ago when we delivered the first vessels back 2011, which were nowadays called the Vale Max. The first generation of those vessels came with a reduction of 35% of CO2 emissions, which is pretty significant. Most of the cases of these vessels was based on scale gain. Those vessels are the largest ore carriers on the world, which can carry 400,000 dead weight. On 2018, we have again a second generation of vessels, the same size, 400,000 dead weight, which also again reduce 41% of emissions. And this is so far the most efficient vessel in the world. In 2019, we created the Guaíba Max generation, which is 325,000 deadweight. This vessel helped us to reduce 38% of CO2 emissions. And all this combined, together with the other vessels on the fleet, we have already reached a reduction of CO2 intensity of 16%. A little bit more curious about what is the Vale Max. The Vale Max is G2 generation, which I just mentioned, which is the most efficient vessel in the world because of the scale, because of the technologies applied, because of all creativity and innovation that we apply on the system, on the vessel. It became unique. We can look a little bit. I think for here is better for me. So we have a special designs on the cargo holds. This vessel can carry high moisture content of cargo. The vessels has scrubbers, which we already treating the sulfur content a long time ago. The vessels has already hydrodynamic devices that also helps the vessel to start to saving energy. And this is, again, a project for over 10 years ago. This is actually a potential road of the low carbon on the shipping business. What we can note is that so far, if you look at the map, it is a scale of the potentiality of emission reduction against the challenge, the complexity, the maturity of each technology. When we look, it's very, we map all the potentialities, but the ones that has high potential for reduction, of course, are the more challenge, and they start to be pulled ahead. And that's what comes the program. The program helped us to accelerate. We wanted to push the industry to move forward, to test, to pilot, to identify opportunities and implement. And if we succeed, we scale. So that's how actually we work. We have the phase, we work together with startups, with more than 2,000 startups. From these 2,000 startups, we have selected 20 very important solutions. And then we partner with laboratories, labs, universities, class, and so many other companies. And then we identify all the potential technologies that, and the maturity level. And of course, we narrow, and until we arrive at the phase C6, which is that we launch the pilot, we monitor, we evaluate, and then we scale. So the Ecoshipping has implemented pilots and collecting performance data developed along the strategy. So we have implemented several technologies already. We have an idea, we do this roadmap that I just mentioned, we pilot, we verify, we certify, we help the industry to get developed, and we propaganda that to the ship owners to say what is worth and what is not worth. And then we have launched already several different types of sales solution, rotor sales, hard sales, in more than 7 different pilots. We have launched several energy save devices as propellers, devices, PSD, VFD, different types of paint, silicone paint, and high-performance painting, and so many things. Hull design. We also, in-house, we have developed, with the partnership with several universities, systems that help us to optimize, systems that help us to monitor performance. I think the biggest pain point on the industry so far is the people implement technology, but they don't know how much this technology really influences the performance of the vessel. And we have studied that for over 6 years, and we're developing in-house systems that can help us with this information, segregating all the technologies on board and give you isolating the performance of each energy save device. What comes next? So we already launched 3 generations of vessels, and this is the 4th one, which we just finished the contract. It is a 2nd generation of the Guaíba Max with the 325,000 dead weight. What comes next on this vessel is everything that we have tested, everything that we have certified, everything that we verified, and is safe, is efficient, and help the industry to engage in a more scale related to the performance. So this vessel has, we call the state of art of a ship, because we put together wind solutions, alternative fuels, and hull optimization, all energy-safe devices that we test and don't conflict with each other. And in addition, painting, and in addition, the vessel is ready for several types of fuel. This vessel brings already from the shipyard as methanol dual fuel with extension from ethanol as well. But as Vale plays on the fuel and technology agnostic, it means that we believe that everything is possible. We just start from the most mature technologies. Then we start from these 2 fuels, which is much more mature nowadays, but the vessel is ready to be retrofitted for other fuels like ammonia or LNG. So I know that everybody wants to go to the coffee break. It's been a long day. So my final considerations here is Vale is committed to sustainable solution, energy transition. It's the heart of our strategy. Vale has made significant achievements in line with its commitment, has fostered an environment of cooperation partnership to address the challenge and climate change. Thanks so much.
Thank you. Thank you so much for bringing this very, very important topic to our attention. I think this really added or contributed to the richness of this Breakthrough Technology Conference. So let me turn to our audience first and ask if there are any questions coming from the audience. Let me kick off then. This Guaíba Max, right? Guaíba Max, I'm sorry. So, how is it a collaboration with shipbuilders, or do you collaborate with ship owners and then they collaborate with shipbuilders? So, how did that process work? Do you directly collaborate with shipbuilders?
Okay, thank you. Actually, a very good question. We normally start everything in-house. We research a lot. We have ideas, we research a lot. We have a big group of naval engineers. We are not even ship owners. We don't own any vessel, but we partner to the others to build ships in our specification. So we design the ships, we test the technologies in partnership with owners, and we invest eventually as well. And then when the technology is validated and the numbers start to make sense, we bring back to our projects. And our projects are in-house for really long with ship designers, with class society, with shipyards. We do a lot of this in-house. When it's mature, then is the time that we go to the ship owners, say, I have this project, I have an idea, who want to join me on the journey? And that's how we call it, we tender to the market. We do in a very open and transparent way, so that people feel challenged to collaborate. So we have several different ship owners in the world that come to us to develop our own projects. Of course, ideas grow out of that, because we can design, we can believe that we have the best design, but we always welcome ideas, and eventually it's a big, beautiful marriage, and the vessels comes even better. But replying your question, everything starts in-house with partnership with consultants and designers and class.
Quite impressive, I should say. Well, any questions? Yes, please. First.
Thanks a lot. You mentioned you don't own the ships. Are you in some way or form involved in what happens with the ship at the end of the life?
Very good question. Yes, it's if the ship, most of the ships in our fleet, they are in voyage charter. So but they keep coming because they are special. There is a huge family of vessels nowadays on the same characteristics. The contracts can go in a very long period, and owners can choose which the vessels they will nominate into the contract. But it doesn't matter how long the vessel stay in our contract. We have very robust clauses in our contract, making sure which kind of partners we work with. So we vet how the companies handle the ships from the beginning to the very end. We vet not only about one ship itself, we vet about the process and procedures of every single partner that we board in our program.
Thanks a lot.
So, yes, Edwin, please.
Thank you. This is very interesting. I've just one question. In all of the solutions we've discussed yesterday and today, although we did not always say this bluntly, but there is a cost element, an additional cost element of decarbonization, and the challenge for the industry would be how we drive this down. With your decarbonization impacts on the shipping, do you find the same thing? In other words, has decarbonization a knock-on effect in terms of the shipping rates that you can charter over a 20-year period? And do you have solutions on how to bring this down back to, let's say, normal rates again?
I think that's the big question mark of the whole industry. You touch a special point. Well, yes, of course, that innovation has a cost. And I think that's why we have so much setbacks for many people, because it has a cost and it doesn't pay back in the very moment. So, but we have a target so ahead, our targets are so robust, so ahead, then of course that's what we do for the industry. We sponsor projects because owners hardly will start by themselves, because it's costly and doesn't show the payback immediately. But as the time goes, the targets start to get tight, and probably taxations comes and so, and then you'll start to see results. But decarbonization is not about costs, right? It's about decarbonize the world. So of course it will be costly, and I think that's the main balance is how we're gonna redistribute all these costs along everybody, that nobody take the big burden. But it's everybody's responsibility. It's a social responsibility from all. So I think, yes, that's why we step ahead and we sponsor projects, because we know that the first step is very hard, it's costly.
I see we are almost completely running out of the coffee time as well, so maybe it's a good time to conclude this session. Michel, Alexandre, thank you so much for this very interesting contribution once again.